Alright, hello, my name is Miguel. I am part of Ozbay's class for summer 2025 of fluid mechanics. This is the final project. Um, yeah, this will be part B. I did part C in here already, but we're going to do part B right now. For part B, we're going to use fluid flow fluent. The subcase is pretty easy to use. And now we're going to open it up. Alright, we're here. Just like part A, we're going to replicate the same wind tunnel geometry. Go here, 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 here. And just place them. It doesn't really matter right now. Okay. Yeah. Okay, it's connected. That's good. All right. First thing I'm gonna do is make all this symmetric. There you go. Looks good. Now we're gonna dimension all this. Now, according to our project, I'm gonna state the dimensions right now. This guy will be 1.2192. From here to here will be 1.5748. Then here's 1.1176. 1.626. Okay. So this one 0.06. No. 0.6096. There we go. And then finally we're gonna get 0.889. Okay. Dimensions are all in place. Now I just gotta center it. Easy way to do is just make a line from here to the midpoint. It's just a construction line. And then I'm gonna make it vertical. There you go. That looks good. Now, what we gotta do here is, since we're gonna be simulating a cylinder inside the wind tunnel, or a circular cross section inside a wind tunnel, we're just gonna make a circle. And then the diameter will be, according to assignment, 1/10 the height of the wind tunnel. This is just so the walls of the wind tunnel doesn't affect our results, because if it's this big, then you're gonna have a lot of air going really fast in here because of Bernoulli's principle, and then the air around here is gonna be a lot faster, and it's just gonna affect your results. So we're gonna dimension this. Now, our height of the test section is 0.6096, and then we have to divide it by 10. Then we get a diameter of approximately 0.06096. There you go, looks good. Just like that. And yeah, it's in the center and everything looks good. Now you could press D, or you could click 3D mode. I'll press D, it's quicker. And then click on the edges you're interested in and name them. So you press Control G. Click on the edge and press Control G. So inlet, away. Click the outlet, Control G, outlet. And then we just repeat this. Name this guy low. And then this one will be top. And this guy will be a cylinder. It doesn't look like a cylinder, it's a circular cross section, but you see what I mean. Okay. Now that all looks good, we could just leave the discovery and then go straight on to meshing. Okay. Now we're here in the mesh. Now we just gotta do our meshing. Now for our mesh, we're gonna insert several different refinement options. First thing we're gonna do is do our sizings for the nozzle. Here, leave it like that for now. Set up a bias, and I'm gonna use a bias factor of 3. Now you can see where the bias is pointing towards. Pardon my mouse cursor here. This needs to be reversed, so you click on reverse bias, click on the edge, click apply. There you go. Now we could number divisions, and I'm going to go 200. There you go. We do that afterwards so we can see how the bias works. Name it. Nozzle. Insert. Sizing. I'm going to do the diffuser next. And it's the same thing. So repeat the same thing. Same settings and everything. Diffuser. Next, we move on to the sizing of our test section. And this we'll just set as 250. Okay. Next thing we gotta do is a sizing on the cylinder. So for this, see if I remember correctly, this will be, let's do 100. Let's go 200. Why not? 150. There you go. No bias. Curvature normal angle, let's put that to 10. There you go. And then there you go. Looks good. Next thing I'm gonna do is put a method, click on the whole thing, and we're gonna use triangle. There you go. Then after that, we will be doing inflation. Click on the face, then click on the geometries, or you could click name selections, and then we're gonna go with the top and lows. The cylinder will have a different parameters, so we're gonna do that in a bit. This one we'll do limit wind tunnel boundary layers. Insert another inflation. Click on that. First layer thickness 1e -5. Don't think I did that. Yep. The same thing here. First layer thickness 1e -5. Layers, I'm gonna go with 60 layers and a growth rate of 1.1. For here, I am going to do 80 and 1.1. We might need to go back and change this. Can't really remember what parameters I used, but let's go. So cylinder boundary layer. There we go. That all looks good. And now we go back to the mesh, element size 0.005, so 5 millimeters. And then we generate. Okay, the mesh is complete. Looks good. I think 80 might be a bit much. We're gonna reduce it just a little bit. Let's go with let's go with 70 and generate. Okay, looks much better. I like that. So yeah, 70 boundary layers is the way to go. Yeah. So we're done here, and we're gonna move on to the setup. Okay, now we're here in the setup. Let's look over through this. We're gonna be using K Omega as our turbulence model. It's pretty versatile, so we're gonna use it. No, don't really have to mess with that. Materials, we're leaving it as default. If you want to look in here for calculations, but we're gonna leave it as default for now. Cell zones, yeah, that's okay. Now here, the inlet, sure it's already mentioned, but the velocity magnitude is calculated from the ratio between the height of the inlet and the height of the test section, and also the ratio between the inlet velocity and our target test section velocity. For this assignment, we need a test section velocity of 15 meters a second. Now to calculate that, you use, what was it? V2 divided by V1 will equal H1 divided by H2. Yes, that's what it is. And if it's 3D, then instead of H, you'll be using area. So, yeah. And calculator result will be 5.625 meters a second. Do keep in mind that the flow will not be uniform. This will probably be around the average-ish around there. What will be like 15 meters a second will be like around here, but the velocity in the middle here won't be, because we have a viscous physics model. So yeah, but regardless, it's okay. We use 5.625, and then now we could check if everything here is okay. Internal outlet is good. The walls are fine. Okay, and then now reference values. You don't really need reference values. I am just going to have them here for now. But you really don't, because if you want to calculate your drag coefficient, which is what we need, if you compute from inlet, the value would be off because your reference value would be from the inlet, like the velocity, the area, and that just won't be accurate. You want your reference values to be in here on the test section, but we can't do that given how it's set up. So instead, what we're gonna do is just calculate it with the force reports that we would get from the simulation. So, but I'm gonna leave it as inlet for now. Just leave it there, just in case. But you won't really need it. Now in here, you could go new force report, and what we're interested in is the drag force. Okay, cylinder, and then drag. Okay, make sure, of course, the force vector is correct. That's fine. I'm gonna print it to console and click OK. All right. Now that that's done, we could go into residuals. I'm gonna set this as 1e -4. May or may not reach there. Not sure, because this is a cylinder. It would be very turbulent with the wake around the rear, so it will be harder to simulate. Turbulence is always very tricky to simulate, but we could always try our best. So I'm doing 1E negative 4. Just it would probably run quick or not. Go. And now we could initialize. All right. Yeah. Okay, finish initializing. Now we could run the simulation. I'm gonna put this 1,000 iterations, but most likely it will cut short of that because of our convergence criteria. All right. Now I stopped it at 400 because it looked like it already converged. Yep, it pretty much already converged. So I wasn't gonna go any further. So I didn't see a point going on further. So that's done. Now this could mean either one, it's just turbulent, it's just normal or natural, or two could be the mesh. We could check the mesh right now. Now we're using K omega, and the thing is that with K omega and also probably K epsilon as well, not too sure. But I know for sure that with K omega, you need your wall wide plus, which is a turbulence parameter. Your wall wide plus has to be under 1. It has to be below 1, okay? And it should be below 1 for anything that's like not supersonic. Anything that's like low speed should be under 1. So if not, then you're gonna have to mess around with your boundary layer mesh. So right now you could check your wall wide plus if you go here, contours, wall wide plus, and then click on the cylinder. No, not wall fluxes. This is turbulence, and then wall wide plus. On the cylinder, click OK, and there you go. Now you can see our wall wide plus is actually pretty good. The red, the high spots, is only 0.5, like 0.524. That's really good. I'm pretty happy with that. So that our mesh is good. It's just naturally with the turbulence, which is to be expected, which we could visualize here. Velocity. Actually, just for curiosity, this isn't for the project, but rather just because we're curious. Let's look at kinetic energy. Yep, as expected, you could see the turbulence going across like that. So now this is just not part of the assignment, but that's just curiosity. You could just see the turbulence, the kinetic energy of the turbulence. So yeah. Now back to the assignment. Well, the project. We need our velocity contours, which is very simple. Just could be velocity. Yeah, you can see right here. So that's our velocity. Next, we need static pressure contour. Looks good. And then here we're gonna do total pressure contour. Yep, looks fine to me. Dynamic pressure contour. Yep, looks really good. Let me see what else we need. Total, dynamic, static, and velocity. That's all we need. Alright, good. It's alright. Those are all our contours that we need. Next is on to the plots. Here we go. Now for part B, which is what we're doing, we need our coefficient of pressure along the surface of it. So pressure, coefficient, and here we're gonna go what? No. We're gonna get our static pressure along the surface. Now we need our coefficient of pressure. However, there is an issue with this, and that is that our reference values are not correct. Our reference values is from the inlet, not from the test section. We can't really set it up in the test section. Well, sure there is a way, but I don't know how to do it. So instead, we're just going to plot the values, export it, and then put it into Excel. So save and plot. We're going to need our static pressure, and then with that static pressure, then we could get our pressure coefficients. So yep, that looks pretty good. It's fine right there. And yeah, I'm pretty sure that's it. Well, other than I guess drag coefficient, which you just compute. And then once you see this drag coefficient, then you plug it into the drag coefficient formula, which I can bring it up here. The drag coefficient formula, this is from someone from the class. Drag coefficient formula for cylinder, that will be right here. Drag force divided by 1/2 density times velocity in the test section squared times your diameter. So you plug that in there, and then you could also get coefficient pressures right here. This is your coefficient pressure. So you're going to use this equation to get your coefficient pressure graph as well. Yeah. But for that, we have to export it to Excel and then manipulate it there. But that's it. Thank you.